Welcome back to Mechatronics 1320, Mechanical Components. We're skipping ahead here to Chapter 14, and we're going to get right into gear drives. Okay, so we're going to spend a lot of time talking about gears, different gear types, how they transmit mechanical power, how they change speed, how they affect torque, all those different avenues, where we can possibly use certain gear types and things like that, all across the board. So, if we take a look at, what is a gear? Well, it's a toothed part that meshes with another toothed part to transmit power, change speed, or direction. Okay, we can also use it changing speed, but that also affects like torque and things like that. So there's where we can kind of get our larger gear drives. Okay, the larger the two gears here is referred to as the gear, and the smaller one is called the pinion. So if I use the term gear, we're talking about the larger gear. If I use the term pinion, we're going to talk about the smaller gear as I go through all the vocabulary and explain everything here. Okay, so different dimensions of a gear. So we'll take a look at these in a lab and do some measurements on a gear and things like that as well. But it's important that we understand the different parts. Okay, so if we talk about the face width in the bottom right-hand side of the diagram here, that's how wide that gear tooth is, Okay, then we have circular tooth thickness. Okay, see kind of where the angle goes. It's generally on what we call the pitch diameter or when we take a look at that, but it's just the chunk of the tooth there and how wide that is on that aspect. Okay, we have the tooth space width. Okay, so the tooth space width, you can see that's in the upper left-hand corner. That's the distance between the teeth on the gear. Okay, that also lies on the diametral pitch as we do that. Okay, the pressure angle is the angle that the actual tooth makes, and that's where the teeth mesh together. Okay, so we're going to talk about that in a little bit, but you can kind of see there. It's on the right-hand side, the tooth pressure angle. All right, but that's where we're going to have the gears mesh. Okay, the outer diameter, that one should make sense. That's the widest diameter from the tip of one tooth to the tip of the other tooth. Okay, we have the base circle diameter. Okay, so if you take a look there, that one's probably just called base diameter on the graphic up here, but it's pretty much just to the inside bottom part of the tooth. All right, and remember the diameter is the distance across the circle. So anytime we use diameter, we know that we are dealing with the distance across the tooth. Okay, the addendum. Okay, there's two parts. There's an addendum and a dedendum. The addendum is the upper portion of the tooth that encompasses the tooth pressure angle. All right, and the dedendum is the distance between where the tooth pressure angle starts or all the way to the depth of the tooth. If we talk about the whole depth, okay, that's the entire depth from where it goes into the groove all the way to the top of the tooth. Okay, so that one's shown on the right-hand side of the diagram here. All right, number of teeth, that one's pretty plain and simple, right? We are going to count the number of teeth on the gear, or it's written on the gear. That's going to be very important when we start talking about gear ratios because it's a ratio of teeth. 11 is the pitch diameter, and you can kind of see where or we can call it diametral pitch, but where it goes through the center of the tooth or where the tooth pressure angle begins. So it's kind of the center point or the splitting point between the dedendum and the addendum as well. So that's the pitch diameter. We call it that because that's where we want the gear to mesh, and that's where the power is going to be transmitted, or the speed or the torque that's going to be transmitted back and forth. Okay? And that's pretty much the ins and outs and the content knowledge here on the gear itself. And we'll do a lab where you got to take measurements using a dial caliper so that you can understand all these different parts here. But let's talk about circular pitch here, okay? The distance between one point on a tooth and the corresponding point to the next tooth. Okay, so the distance between one point on a tooth and the corresponding point on the next tooth. Okay, so that's our circular pitch. Because Notice that the teeth don't go up straight. They're not perpendicular the entire way out of that circle. So that's why we have to be able to calculate this. And this is important in circular pitch so that we can understand how to make sure that our gears mesh together correctly. So one way of finding that is taking circumference, that's of the gear, right, 2 pi r, divided by the number of teeth, or we could just take pi divided by the diametral pitch. All right, so those are two different ways that we'll go through and do those calculations. All right, the pitch circle of a gear, that's located on the gear where the speed and the torque are transmitted. All right, so we call that, we use the two pitch circles because that's where we say the gears mesh, and you want the gears to mesh properly so that we can transmit our power through it. All right, so at the point where the gear teeth along a line that passes through the line of centers of the two gears. So if you look at the diagram here, in the very middle of it, where we're trying to mesh together, transmit power. So we want our pitch circles to line up, okay? So it's only significant, okay? The only time we really use the pitch circle in determining the pitch diameter, okay? Determining the pitch diameter. So why do we use the pitch diameter? Okay, that's where we calculate the speed and the torque to the driven shaft. We have a driver shaft and a driven shaft, and we're going to get into that here shortly. Okay, but let's break down the pressure angle, okay? We talked about it a little bit ago, but that's the angle that's passed from one tooth to the other. The most common pressure angle, okay, is 20 degrees. And you can kind of see in the picture, right? That's where we have, the tip of the tooth of the gear starts to, turn inward, so it looks like a teeth, like shark's teeth or things like that. And they're not as sharp as that, but you can kind of get the idea. Okay, backlash is very important. Okay, that's the space between the non-driving sides of the gears. So that's so you want to have enough backlash so as you're rotating the gears, it can clear out. So as it's transmitting power to one, it's got to clear out of the other gear. And we're going to talk about how to adjust the backlash. And you guys might run into this in your labs as well, where you either have too much backlash and the gears won't turn, or will not turn. I'm sorry, they will turn. And then if you have not enough backlash, all right, they won't touch each other and things like that. So root clearance, okay, that's the radial distance between the top of the tooth of the pinion and the bottom tooth of the pinion. Okay, so let me step back to backlash again real quick. Okay, you have to have a certain amount of backlash so that the tooth, clears as they mesh together. Okay, if you have too much backlash, the teeth probably aren't going to touch each other. If you have too much once again, I'm going to start that one over. When you have too much backlash, okay, there's a big space there. Your gears will probably most likely not even turn, okay, because they won't even touch each other. They won't even be able to mesh. If you have too little backlash, the gears are going to lock up because they're going to get stuck on one another. So, sorry, hopefully that clears it up. But what I just said, that's how I want you to understand and interpret that piece. All right, so let's talk all about a gear drive. What's a gear drive? Well, we're actually taking two gears, meshing them together, and we're either transmitting speed or torque, okay, or power in those kind of forms. So when we talk about gear ratio methods, there's a couple different ways we want to be able to use a ratio to talk about when we're transmitting speed or torque. One is we can use the ratio of the pitch diameters. The other is we can use a ratio of the number of gear teeth. Okay? Now, in real life, you can look up the manufacturer's catalog as well and see how many teeth are on the gear, so you don't have to sit there and count. Sometimes they may or may not be labeled for you as well. So how do we calculate that? Well, we have a driven gear and a driver gear. Okay, the driver gear is the one that's doing the majority of the work and transmitting to the driven gear. It may or may not always be the big one or the small one. You can't say that the driven gear is always the big gear and that the driver gear is always the small gear. That is not truth all the time. Okay, it just depends on the application that we want to do. Okay, so don't get locked into that piece. Understand driven or driver, or I like to think of it as output over input. That kind of relates to everything else. So if we take a ratio of pitch diameters here, all right, G, okay, that's our ratio. It's the pitch, okay, the pitch circle of the driven divided by the pitch circle of the driver. Okay, so output over input. So in this case, if we take a look, right, the pitch circle, right, that's kind of the center point on the tooth that goes around in a circle, and we have that diameter. In this case, it's going to be 4 divided by 2. Okay, so we can either use 4 divided by 2, or if we're using teeth, we can do 22 divided by 11. I'm just looking at that first diagram in the upper right-hand corner. Okay, so our gear ratio would be 2. Okay, so we can also do it in terms of output torque over input torque. Okay, so we can base it on that as well. If we look at the next one here, we've got 28 divided by 10. Okay, our 28s are our output, and our 10s are input. Okay, so we have output over input, so 20 over 10. So our gear ratio is 2.8, and that gear ratio is going to be very important when we start talking about torque and when we start talking about speed with gears. Okay, and then sorry if we do the last one, right? We have the driven there is 30 divided by 60. So in this case, it's 1/2. Okay, and take a look at the speed. Okay, on that animation on the left-hand side, notice that the driven one is going twice as fast as the driver. Twice as fast. So that means the driven is going to spin around 2 times, and the time it takes the driver to spin around once. So very important that we understand that, because it's talking about speed, and we're using the gear ratios for speed. So that's a good example where the driver's the larger gear, okay, and the driven, okay, is the smaller gear. So like I said, don't get locked into saying that the big gear is always the driver, the small gear is always the driver. Don't get locked into that sort of thing, okay? It just matters on what we're doing. Sometimes we want to speed up, sometimes we want to slow down. So it just depends on where we place that gear. Okay, so the gear ratio determines how fast the driven gear will turn. The teeth of the driver gear transfer speed to the teeth of the driven gear. Okay, 2 gears at their pitch diameters move at the same surface speed. Okay, so even though the smaller gear is moving at 1800 RPM and the larger gear is moving at 900 RPM, okay, at that surface speed, or at that point of contact, the mesh point, that speed is the exact same at that particular point. But we transmit that based on ratios. So output over input. So we can see this as either the input speed is twice as fast as the output speed, right? Or we can say the output speed is half the speed of the input speed. So you can kind of change your verbiage on, depends on if it's your output or your input. So different size gears have different RPMs. Larger gears will always have a slower RPM. Smaller gears will always have a faster RPM when we're doing calculations, okay? Other aspects of a larger gear. Larger gears have smaller RPMs. So that means torque goes up, speed goes down by whatever the gear ratio is. Okay, so that gear ratio is a multiplier. So always think of output over input. Speed and torque are inverses of each other. You have to give. As torque goes up, speed has to go down, or as speed goes up, torque goes down. Think of a 4-wheel drive vehicle. You have 4-wheel high, 4-wheel low, and you have 2-wheel drive. You leave it in 2-wheel drive, right, as you're cruising up and down the road. And then you have 4-wheel high so that you get more torque, right? You have all 4 wheels turning at the same time, but you don't drive as fast. There's limitations on 4-wheel drive high. Then if you're, climbing a hill or pulling something tough, you might switch into 4-wheel low. You cannot go very fast in 4-wheel low because you're trying to get much more torque, all right? You get stuck in the mud. You want to increase your torque, not your speed. All right, you got to be able to turn and get out of that. So that's the important part when we're talking about gears and ratios and how speed and torque are all affected. So let's talk about the diametral pitch. We mentioned it a little bit. The ratio of the number of teeth on the gear to the pitch diameter. Okay, this is going to come in important here when we do a calculation, because we have to indicate whether or not gears can mesh together properly in order to transmit power and speed correctly. So The PD, that's the diametral pitch. So we're going to take the number of teeth divided by the pitch circle. So, very important test question here. Two gears must have the same diametral pitch in order to mesh. I promise you that will be on a test. Two gears must have the same diametral pitch in order to mesh. Okay? And you want them to mesh so that we have maximum power transfer. All right, so we use it to determine if the diameters or different numbers of teeth have the same size teeth can mesh properly. Common sizes for diametral pitch, right? Remember, we have standards. It's not somebody's going to make their own custom gear or things like that. Common sizes are anywhere between 3 and 48 for the diametral pitch. So we can also do it in metric. And in metric, instead of calling it diametral pitch, they call it the gear module. So it's the pitch diameter divided by the number of teeth. You can also pull it off a vendor data sheet. So this is a vendor data sheet here. Okay, notice the common pressure angle up there is 20 degrees, very common angle on gears, and it gives you all the different specs. Okay, and you can go through, you can see if we want to look at stainless steel versus aluminum, it tells you what the number of teeth are. Okay, and it has the PD, the pitch diametral, and the overall diameter of it as well. It gives you the bore length that we're going to talk about. So lots of important information that you need to know about this. All right, different face widths, that sort of thing. The bore length is important because you got to be able to mount it on the correct size shaft. Okay, so the bore is the hole through the gear there. So very important when you have to go through like a vendor data sheet to make sure that you're buying the right gear or replacement or you're designing things correctly. Okay, and you've heard me mention this already before. Okay, using the pitch circles here, all right, to mesh properly and where the backlash actually lies. Okay, so as long as gears are adjusted so their pitch circles are tangent with each other, the gears will have a correct amount of backlash, right? Tangent meaning that we are hitting each other at one specific point, not a whole bunch of points at once, all right? And they're able to clear and get through. Okay, you can adjust the backlash, and you're going to do this in one of your labs, by adjusting the position of the gear shafts. So for you guys, when you have to make your gears mesh properly, you're going to have to adjust the shafts before you tighten them down. So as you increase the center distance, the backlash becomes even greater. Okay, so let's figure some things out here, how we actually calculate backlash. Okay, a couple different things. We need to calculate the diametral pitch. Remember, that's the number of teeth divided by the pitch circle diameter. And then we have to calculate the center distance. And then we're going to use this chart. This chart's in your book. So you'll be able to do that. And it's also a chart that's kind of all around for coarse pitch gears, so you can Google it as well. But you can have the pitch diameter of gear 1 plus the pitch diameter of gear 2 and then divide by 2. We're really just finding the average there. That's the center distance, but we're finding the average. So let's do an example here. We have gear 1 that has 47 teeth. Okay, it's got a pitch center of 10 inches, and then our other gear has a pitch center of 13.5 inches. Okay, so we have to find that center distance first. Okay, that center distance is finding that average. That's 10 plus 13.5 divided by 2, so we get 11.75. So we're going to go over to the chart on the left-hand side, see where it says 5 to 10, 10 to 20, 20 to 30, 30 to 40, so on and so forth. For the center distance ranges, our center distance is 11.75. Okay, so it's going to fit in the 1, 2, 3rd row down under center distance where it says 10 to 20. Okay, then we have to find the diametral pitch. Okay, so we're going to take 47 divided by 10. Okay, best on the equation in the upper left-hand corner. So that's 4.7. So now we match the row and the column up. So we're going to be the 3rd row down and the 3rd column over that's between 3.5 and 5.99. So it tells us our proper amount of backlash needs to be somewhere between 0.02 and 0.03. Okay, so there's how we calculate backlash. Okay, you're going to do that in the lab. We're going to use the dial indicator, and you're going to be able to move that as you set it on there and move the gear so that that distance, and you're going to measure that distance by turning one gear a little bit till it hits the other gear. Okay, so you're going to be able to take that, and here's what it's going to look like in the lab. Okay, so you can put it on the bezel. You're going to move the gear and rotate it back and forth, and as you rotate it, you're going to watch what that distance is. So notice that the dial indicator's on the back side of the driver gear. You're going to rotate it back and forth as it's connected to the driven gear. So you're going to move that so that it has, in our case, whatever case you're going to get in the lab, but in this case, I'm going to step back, right? 0.02 to 0.03. So somewhere between there on that dial indicator, you're going to move that so that the gears mesh properly. Okay, so this is the setup that you're going to do in the lab when you do this. All right. So how do we know? You can visually inspect it as well. If we look how tight together the gears are in the top picture here. They are so tight together that those gears aren't going to turn. The one gear is not going to escape after we transmit power. So the backlash is less than needed. We need more backlash there. In the middle, we're adjusted properly. The gears can mesh, and the trailing gears can exit without contact. If we look at the bottom diagram, we have too much backlash, and the gears aren't even going to touch each other. So it's something that you've got to adjust in your labs. Okay, so more than likely, you're probably going to have the first scenario where you have too much. Okay, you have the gears too close together, and you don't have enough backlash for them to clear out. All right, let's talk about idler gears. So in general, idler gears, we put those between an input and an output gear, and their whole purpose, okay, is to change the rotational direction. That is it. The idler gears don't affect the gear ratio, the power transfer, or the speed. An idler gear, it's kind of like when you're sitting there, in your vehicle and you have it turned on, but you're not driving anywhere. It's just sitting there idle, not affecting anything. Same with idler gears, okay? All right, so let's take a look at some examples here, all right? We have gear A, that's the input. Gear B is the idler gear here, and gear C is the output. So if we take all the different gear ratios, so if we look at the gear ratio between A and B, but it is important to know the C is the output, okay? B, even though it's an idler gear, it's the output for A. So just know that if we pair these up, there's always an input and an output. So even though gear B is the idler gear in the whole system, gear B is an output for gear A, and gear C is an output for gear B. But if we take a look at the gear ratio here between A and B, all right, it's 21/13. The gear ratio between B and C, okay, between B and C is 42/21. And then the gear ratio between A and C, okay, is 42/13. So just for reference, right, the first ratio is 21/13, okay, which is 1.61. The second ratio between B and C is 42/2, which is just 2. And then the last ratio, all right, A and C, is 3.23. So out of all of that, all right, which gear supplied the largest torque? Obviously C, right? It's the largest gear. The larger gear will always have more torque. Okay, which gear rotates at the highest speed? That's going to be gear A. Okay, it only has 13 teeth, so it's going to rotate the fastest. All right, so all important information about gears. Okay, so we can look at different gear types now. Okay, there's spur gears, helical gears. So I have a diagram for each one. Okay, so if you take a look at spur, we're going to get into each one in depth, but I want you to see, look at the teeth and how they're shaped or what direction they go and those sort of things. So we got helical gears, double helical gears. Okay, that's a big one. Double helical gears are also called herringbone gears. So notice how there's like a V in the center of those. Okay, there's bevel gears. Okay, so there's where we can transfer 90 degrees. There's worm gears. All right, and we have a different kind of example we'll go over in each class of the different types of gears and things like that. But let's take a look at spur gears. Okay, they are simple in construction. They're very low cost. They can have external teeth or internal teeth. So a planetary gear is shown in the bottom right-hand corner. That's internal teeth. Okay? The little ones have external teeth, but the large one on the outside, okay, that has internal teeth. Okay, we can put teeth on a rack and pinion type scenario. All right, the disadvantages of spur gears are they generate high friction, so we want to use them with only slow or moderate speeds. And then as their velocity increases, vibration also increases. And remember, vibration creates damage, okay? So, I mean, we do lubricate those and things like that as far as like when they're in enclosures or outside. But, you know, as velocity increases, even lubrication is not going to stop the vibration from happening, okay? So, you can kind of take a look at, you know, if we have rack or pinion or thing like that, you know, we can use it to turn a cart or things along those lines, okay? So that's the rack and pinion on the right-hand side with the steering wheel. Let's talk about helical gears. They have gears on parallel shafts, and they have to be of opposite hands. Okay, so they're on parallel shafts and opposite hands. So when we talk opposite hands, we're talking about, look how the angle slides down from the right to left on the right-hand side and from left to right on the left-hand side. Okay, so they run quietly and smoothly than spur gears. They're much more efficient. We can run these guys at higher speeds, okay, because of how they're sitting on parallel shafts and opposite hands. The vibration is not as bad as it is with spur gears. And we can carry higher loads when we compare them to spur gears. Some disadvantages, though, are they create thrust loads in one direction, right? Because of the parallel hands or the opposite hands on the parallel shafts, we can create a thrust load instead of a vibrating load. And these are obviously more expensive because of making the opposite hands work on them, okay? But some different pictures for you to get an idea on what to look at. The double helical and herringbone gears, same gear, okay? But notice now we have more of a V. We have the left and right hand kind of put together. Why do we have these? They handle extreme loads. So you're going to see a lot of these gears in like mining operations and things like that, where we're transmitting large loads. The actual thrust that was with the bevel gears, that's canceled because the left and the right hand are meshing here. So we don't have to worry about that issue. The disadvantage, these are extremely expensive, right? There's a lot more precision that goes into making one of these gears, and they are very sensitive to misalignment, obviously, okay? If you don't precisely align these, there's a lot of damage that can be done to them. All right, so bevel gears, right? We use a bevel gear to, we can use them as a straight, a spiral, or hyporoid kind of design, but what we really do and what they're important for is we make an intersecting angle at 90 degrees, all right? So we change our shaft from something that might be vertical to something horizontal and vice versa, okay? The disadvantages of these are they have low gear ratios and the shaft bearings have to support the load, okay? And part of that just because they're coming at 90 degrees. And they require complex and very precise installation there, okay? You can obviously see because we have to make sure the teeth align correctly. All right, worm gears. So there's a picture of a worm gear. We also have one on station 7, I'm sorry, it's station 3. All right, and I'll show you guys that on the 870 trainer when we're looking at it. But worm gears, they run very quietly and very smoothly. They're resistant to shock loads, and they have very high gear ratios in a compact area. So, no shock, very high gear ratios for us. Disadvantages, though, they're low efficiency due to high friction, resulting in a pure sliding action. Okay? Worm gears should only be the input, and the gear should always be the output. Okay? We cannot make them go the other way, so that's kind of a disadvantage of them. The worm gear is only the input. That's a test question, just so you know. Worm gears will always be the input gear, and that big gear is always going to be the output, okay? And they're only going to spin in one direction. You're not going to back out with those, okay? So, some basic questions here. What are 4 types of gears that we talked about? So, pause this, see if you can answer them, and then we'll kind of go through it. All right, so spur gears, helical gears, bevel gears, and worm gears. Why a helical gear can carry more load than a spur gear of similar size? Okay, it's because of the two meshing teeth, all right, the double helical or the helical, all right, and it takes care of the vibration. Well, not the double helical, that's a herringbone, but all right, the contact area is more. Okay, so that's the advantage of the helical gears as well. All right, true or false? A worm gear must be used to hold a load or to prevent a system from reversing due to its self-locking tendency. That is false. All right. Moving forward here, as a rule of thumb, gears should mesh such that the pitch circles are tangent to each other and they should not be intersecting nor have no point of contact, all right? I've mentioned this multiple times. Just want to make sure that you guys understand this when we align gears, especially in your labs, okay? So lastly, let's start talking about gear wear and tear and failure and those sort of things, okay? Most of the time, gears, when they start to go bad, it's just because of loads, right? Continuous overloads, shock loads, vibration, just constant use when we go those. Sometimes harsh operating environments, okay? Sometimes they're outside, right? You got all the different elements, oxidation, rust, dust, sand. Any contaminant gets between there, all right, and ruins the metal on metal contact. Or, lubrication, okay? Failure to lubricate or those sort of things. Bad insulation. Okay, sometimes you're going to notice on some of the gears, they might be worn on one side because the alignment wasn't good. Okay, so all those different things can cause failure in a gear. Okay, so others, right? Surface fatigue. Remember the gears heat up as you're using them. Heat up, cool down, heat up, cool down, different things like that. So different stresses can occur on the material. Okay, wear. Uniform loss of material due to lack of, lubrication. When you have metal on metal contact, it is going to wear something out. So it's very, very important. Okay, plastic flow. You guys don't think about gears, but if you, where they all are, they're not all metal. There's a lot of plastic gears in printers and copiers and those sort of things. Plastic, as it heats up, all right, it becomes deformed. Or, if there's obviously when you're using plastic gears too, you're not using a bunch of lubricant, so the plastic is going to wear over time. All right. Also, breakage due to fatigue or stress cycles. Okay, shock loads, but misalignment's a key one. All right. So let's talk about enclosed gear drives. Okay. What we're really talking about is a speed reducer or a gearbox, and I'll show you guys the one that we have in class. But a gearbox is technically a speed reducer, okay? So the way everything is set up, all right, we have a shaft configuration, okay? That's a number and arrangement of input shafts and output shafts. They can be in a inline type position or at right angles to one another, okay? The hand of drive, that's the location of the output shaft in relation to the input shaft. And then there's different types of mounting methods. The method by which the gearbox is connected to the prime mover. A common one is foot mounting, shaft mounting, and scoop mounting. But just remember, gearboxes are speed reducers. So there's multiple gears in there to take a speed, all right, and adjust it and fix the torque and the speed based on the number of gears in the box. So always talk about the efficiency when we talk about a gearbox. Okay, always power out is less than power in because there's always a loss when we're converting energy. We have a mechanical rating. Most of them are rated to 200 to 300% for safety. There's a thermal rating. Okay, that's the maximum power torque that can be transmitted continuously. Okay, this is determined by the ability of the gearbox to dissipate the heat. Okay. Horsepower and torque capacity, rated input horsepower. That's the maximum horsepower at the input that can be transmitted safely. Maximum output horsepower is less than the input horsepower. Okay, so important on those. Service factor, that's always dealing with oversizing. Okay, we've talked about that in multiple aspects of things. All right, oversizing the gearbox for longer service life. Remember, the service factor is, it's that percentage that you got to come up. So we talked about that with motors already and how that relates. Backstops. So you can put something in like a clutch or something along those lines so that you limit or prevent, okay, the gears from going the other direction. Now, we can always calculate the gearbox ratio. It's the input speed divided by the output speed. Input speed divided by the output speed. Remember, they're speed reducers, so your output speed should always be less than your input speed, okay? Gearboxes can have single, double, or multiple stages of reduction in them, all right? As the number of stages increases, gearbox ratios increase, but efficiency decreases, okay? So the more stages we have in there, and we're going to talk about, and we've done examples where, we talk about efficiency of a system. So, but as we add more to it, it's not going to be as efficient. Okay, we've talked about overhung loads. Okay, remember those are the ones that are 90 degrees, putting stress and strain on the shaft. Okay, those cannot exceed the maximum load to avoid loss of service life or broken shafts. There's also a thrust loads. Remember, those are parallel to the axis of the shaft. So where do we get thrust loads? Remember, those are from helical gears. External loads, fans, mixers, things like that. You got centrifugal force on fans, all right, and those sort of things. Thrusts result from thermal expansion as well. So when we talk about gearboxes, okay, we have concentric gearboxes. Those are called inline speed reducers. So there's a picture there on the right. That looks similar to something that might be in your vehicle potentially, all right. Single to quadruple reductions. Ratios are typically 1.5 to 1 or 500 to 1. We also have worm gearboxes. They're very compact. They have very high ratios, 3,600 to 1, and you can mount them in various ways. Okay, disadvantage, large amount of heat generated in those. We also have parallel shaft gearboxes, all right, very high loads and things along those lines. But your transmission here, right, 5-speed gearbox, so you can kind of see back and forth how your transmission works in your vehicle. Now, this is for, a stick shift or things like that. Your auto transmission is relatively the same, but it does all this for you. So right now, our gear shift is sitting in neutral, right? So you can push your car. But if we shift to first, remember, it's just changing gears. So remember, your first gear should have probably what? Your larger gear, and your fifth gear is going to have your smallest gear, right, when we're talking speed. So notice how we shift. We shift into first, okay, and we're on the large gear. Then if we come over, we shift to second. So you can see the green line that's showing the output of how the gears are turning right now, and how everything switches. And then we can shift over back to neutral, and we can shift into third gear. So we're able to calculate the different ratios there. All right, when we have the N1s through N12s, that represents the number of teeth on the gear. Not saying the tooth has one and the tooth has, or the gear has one tooth and the other has 12. It's just we have 12 different gears here, all with a number of teeth on them, okay? So if we're in third gear, there's how we're going to, the vehicle's going to transfer power, torque, speed. Fourth gear, straight in line there, and we come over fifth gear, and then obviously we don't go straight from fifth to reverse, but we have our idler gear that's in there, and notice that it's reversing everything and reversing our direction so that we can back up our vehicle. So just kind of a quick, thing through our gearbox and our transmission in our vehicle back to neutral as we're driving through. So we also have planetary gears, okay? There's single stage and differential planetary gears. Remember, those are the ones that have some internal gear. And sometimes you call them a sun gear as well. So we kind of keep those internal as they're going, okay? Gearboxes, planetary gears are gearboxes as well. All right, so gearbox installation and troubleshooting. Every gearbox is going to have a nameplate that contains the rated power ratio and the serial number. Okay, you will never modify a gearbox. You're not supposed to modify them or weld on the case at all. Okay, because you can do a lot of damage to things. The foundation has to be solid and rigid for smooth alignment. Okay, and alignment has to be as precise as possible. So use a leveler, feeler gauges, shims, all stuff that we're going to use in the lab anyways when we mount the motor. All right, and we got to make sure everything is in line and all connected to the machinery, and we eliminate a soft foot. We're going to cover that in a lab. Okay, we're going to use shaft connections, couplings, belts, chain drives, all those that we're going to use, okay, have to be properly aligned. And we're going to go through different labs in class that make sure everything is aligned correctly, and we're going to have all of our different guards in place for that as well. All right, everything needs to be lubricated. So even in our lab, we're going to use some dry lubricant or different types of lubricant. We're going to grease our bearings and that sort of thing as we use these. All right, and gearboxes need to be stored in rust preventative oil, ideally, right? Generally, your gearbox is going to be full of oil itself inside anyways, okay? And, you know, you want to make sure that you keep the operation oil, but add rust-inhibiting fluid in there so that there's no contaminants inside or any way for those gears to rust from the inside out. Completely drain the gearbox of oil, spray its internal parts with the rust-inhibiting fluid. This is if you take a gearbox apart, you're not using it, and it needs to sit there for a while. But you can go back through page 420 in your text and kind of read through that a little bit more as you go. All right, but let's do some end of lecture questions here. We're going to see, and let me know if these are true or false. So maybe pause this, see if you can kind of go through and answer these, and then check yourself. The worm gear is known for its high efficiency. That one's false. Okay, remember that's sliding. The worm gear is doing more sliding, and it's only in one direction, so it's not efficiency. It's very low, and we create lots of heat. Double helical gears can transmit high torques, but they suffer from very high axial thrust compared to helical gears. Well, you should know if it's a double helical gear, they actually counteract, and there is no axial thrust, so this one's false. Okay, axial thrust is canceled out in double helical gears. Spur gears are simple, have a low cost, but their high axial thrust makes them unattractive. Got to make sure we pay attention to all the keywords in here. There is no axial thrust with spur gears. Okay, remember spur gears have vibration issues. Axial thrusts come from the single helical gears. Herringbone gears cancel out overhung load. That's false. Overhead load has nothing to do with gear type. Remember, overhung load is at a 90-degree angle. What is a speed reducer? Okay, it's our gearbox, so that we use the different gears to multiply torque. So remember, if speed goes down, torque goes up. And I'll show you some examples where we have those in class. All right, let's take a look here. What type of gear is shown in the picture below? A spur gear, worm gear, herringbone gear, rack and pinion and bevel gear. If you said worm gear, you are correct. All right, which part is always the input in the gear above? Remember, this is important. This is also a test question. All right, it's always the worm gear. The worm gear always has to be the input gear. All right, when compared to the input worm, the output gear ideally has what? High torque, low speed, okay, and power stays the same. All right, what type of gear is shown in the picture below? All right, remember this is where we're changing, from horizontal to vertical or vertical to horizontal, so you better understand that that's a bevel gear. What's the most common type of bevel gear is a hypoid. I don't think I mentioned that earlier, but now you know, a hypoid in the design, okay? In order for two gears to mesh together, they must have the same module. Remember, that's metric, or the same diametral pitch if we're in standard. So same module when we're in metric. So all of that you've ever wanted to know about gears and more. So now we will do the gear labs on the 950 trainer. You're going to mount the continuous speed motor, or the constant speed motor. All right, and you're going to do some inline gear setups, run them. You're going to hook them up to the prony brake and see how they react to different loads. Else, guys, if you have any questions, feel free to email me, or I will see you in class. Ask them then. Have an awesome day, guys. We'll see you in class.